Okay, so here's example 6. It says a homomorphism can express an analogy between spaces that is more subtle than in the prior example. So if we take the example, the map of example 4 that we talked about earlier, we take the vector and we project it to a single number, right? So we take a vector in 2 space and we project it to a particular number in 1 space in the real number line. Now, if we fix any 2 numbers in R, right, then what we're saying is that there's a vector that maps to W1. But not only that, it has components that will add to W1, so that if we look at the inverse image, remember the inverse image, right? H inverse of W1, what we get is we get this set of all the vectors with endpoints on the diagonal of x plus y equals W1. We sort of saw that before in the last video when I drew it out. Okay? So if we look at this here, what we find is here's the diagonal, this dotted line, that we could take 2 vectors, right? Vector 1 and vector 2. We can add those 2 vectors and we can get vector 1 plus vector 2. So we can think of these W1, well, quote unquote vectors, right? Because they're really just numbers, right? So we can take W1, we can think of these as kind of like vector 1 vectors, or excuse me, W1 vectors. And then we can similarly, we have W2 vectors, and then we also have W1 plus W2 vectors. And the addition property says this, right? So we can add these together, right? So if we add a W1 vector to a W2 vector, then H maps the result to a W1, W2 vector. In other words, H of V1 plus H of V2 equals hold on. That's what I want. That. Okay. We'll come back and do another example.